The MCAT is not a test of your content knowledge. It's a test of your ability to get MCAT questions correct.
Alex, back for some more MCAT podcasts. How you doing, my friend?
I am great. Ready to dive into passage 2.
Passage numero dos. So we've started our breakdown of the Blueprint MCAT Diagnostic after having covered full-length 10, full-length 1, which everyone gets for free with a free Blueprint MCAT account. We now are covering the half-length Diagnostic, which everyone also gets for free. Diagnostic fun. Let's go and jump into to passage number 2. What do you say?
Let's jump into it. So here we have electro spinning is a technique used by industries in order to produce filters, membranes, and tissue scaffolds for implants. Electrospinning occurs when the electric forces at the surface of a polymer solution overcome the surface tension and cause an electrically charged jet to be ejected. The solvent evaporates as the jet travels in air, leaving behind charged polymer fibers that lay themselves randomly on a metallic electrode collector. Oh my, what a lot of words.
Yeah. What do we say about this? I would just go, I don't really care. I hope there's something else in here that's more important.
Yeah, so this is a kind of classic science passage that just throws loads of words at us. What I kind of mentally try to do with my highlighting here is just maybe highlight what I think of as like content hook words. And this is pretty tough to do, like if you're just taking the diagnostic, right? You know, if you're listening to this, you've just started studying for the MCAT, you might say, well, what are these words that kind of tie into specific areas of content on the MCAT? There are a few here that we can point out, right? Kind of content areas that the MCAT expects us to have some knowledge on. So to me, that would be something like electric forces.
Where are we looking at?
Electrospinning occurs when the electric forces.
Okay, yeah.
Second sentence.
Yeah.
Surface tension. And then I'd probably just highlight what does this process end up in? Like, why do we care? We end up with charged polymer fibers. I'd probably leave it at that. Oh, and of course, I'd probably highlight electrospinning, the very first word, just because that's the name of this novel process. Mm-hmm. And that's it. I would leave it at that. I mean, maybe, we're not sure what it all actually means. We have this process. It's called electrospinning. It uses electric forces and surface tension, and we end up with some charged polymer fibers.
Okay.
If we move on to passage 2, we have fibers obtained may have diameters ranging from 0.05 to 5 micrometers. The small diameters provide high surface area to volume and high length to diameter ratios. The process has applications in providing scaffolds for tissue engineering products.
Nice. 3D printing away.
Exactly. Yeah, I think this is a great kind of, if I were to like mentally label this paragraph, I'd probably highlight the word fibers, because what we're really getting here is just a description, just in a kind of expanded description of these charged polymer fibers that we mentioned in the previous paragraph. So I'd probably highlight fibers here, the first word. The range of diameters, 0.05 to 5 micrometers, because often in the Chem Phys section, it'll make us do math with these.
Thanks a lot.
And honestly, I think if you wanted to, you could highlight either the surface area to volume and high length to diameter ratios, or you could just highlight the small diameters provide, and everything we need is kind of following that. I mean, both of these are kind of, I don't know, pretty long-winded ways of saying, like, oh yeah, they have a lot of area on their surface relative to the amount of volume inside them, and also they're very, very long, kind of, again, relative to how wide they are. But I think certainly given this picture, that kind of makes sense. We can see here we're kind of creating a big, long, fibrous string.
Yep. Okay.
And this is what we get in figure 1, right? We get a kind of graphical description of this process.
Yep.
I would look at it for maybe 5 seconds, say, yeah, this approximately lines up with what we've been reading so far, and move on.
Okay.
In the next paragraph, we have the density, conductivity, surface tension, viscosity, and pH of the solution are controlled prior to electrospinning. Density is measured by determining the mass of a known volume of solution. These fibers can be coated with proteins as a method of introducing biological molecules to the woven matrix.
Dun, dun, dun.
I was like, as soon as I saw this, I was like, as soon as I read that sentence, I was like, of course it's the MCAT. They have to tie it into biology somehow. How do we make it biology? We'll put proteins in it.
Nice.
Then we have the encapsulation efficiency. Epsilon is determined by equation 1.
Okay.
What would we highlight here? I would be tempted to highlight coated with proteins. And that introduces biological molecules to the woven matrix, and this key term, encapsulation efficiency.
All right.
And I love that it says that density is measured by determining the mass of a known volume of solution, which is to say, yes, we determine the density just like we determine the density for all things, which is to say we figure out the volume and we figure out the mass.
Yep.
Below this, we get equation 1, which again, I think this is, I'm sure for many people, the kind of first exposure to kind of what math on the MCAT might look like, which can be pretty intimidating, particularly since, it's just letters. Mm-hmm. Again, I would just very briefly note this equation. It's an equation for the encapsulation efficiency, and we get a kind of mini paragraph that describes it, which is to say M sub M represents the measured mass of the protein integrated with the fibers constructed, and M sub E is the theoretically expected mass of the proteins integrated with the fiber. Again, looking at this, I would say, yeah, is that efficiency? I mean, efficiency is typically a ratio in the sense that, we want, if, electrical efficiency is often, useful, useful work done by the electricity relative to the electricity used. I would say this is no different. This is clearly some version of that. Like it's an efficiency ratio. It's the mass integrated within the actual fibers kind of divided by the theoretically expected mass, presumably if everything went perfectly.
Okay.
And then we get, furthermore, the productivity of the process is calculated using equation 2, which looks like here, this productivity term is calculated by the encapsulation efficiency divided by the area of the fibers multiplied by the spinning time. So again, I don't like to overinterpret these. Be like, cool, I know what these terms are, maybe. I'll come back and figure it out more in depth if a question asks me something in detail about it. Mm. I remember when I was first studying for the MCAT, I would spend a lot of time puzzling out figures and equations in the passage, only to realize the questions never mentioned them, not even once.
Yeah. Okay.
Finally, we get an experiment was performed on 3 different fibers to determine their mechanical properties. A 10 Newton initial load and a stress rate of 0.5 newtons per second were used. Results of the experiment are shown in figure 2. The Young's modulus was calculated by analyzing the peak stress that the sample was able to endure without deforming. This is I would probably highlight experiment here, because here's the only situation. It almost seems like we've pivoted somewhat. The first kind of part of this passage was talking about this process, and now we're talking about an experiment. We're testing something. Mm. I would say, what are we ultimately looking at? Their mechanical properties, and I would highlight the numbers 10 newtons and 0.5 newtons per second.
Okay.
I would glance at figure 2. It says results of a mechanical stress test performed on 3 fiber samples. I would say, oh yeah, look, 3 fibers. They look kind of different. I'd be like, oh, it looks like maybe B is the lowest and C is the highest. And I would not interpret it any more than that. Again, if we get a question on it, we can spend the time and really puzzle out and see what it actually says.
Yeah. Okay. All right.
We have question 6. Would you like to do the honors?
Oh, sure. I'd love to. I'm going to rock this one. What is the mechanical work done by the initial load placed on a fiber if the fiber is linearly deformed by 3 nanometers? A, 0 joules. B, 3 times 10 to the negative 8 joules. C, 3 times 10 to the negative 6 joules. Or D, 1.5 times 10 to the negative 5th joules. So, mechanical work done by the initial load placed on the fiber. So, I'm assuming we're going to jump down to the experiment because here's where things are actually being done to the fiber, and it's not just some equations here. The load is going to be, I don't know, we have 10 Newton initial load, stress rate 0.5 newtons per second. I don't know if we need the newtons per second because we just want the initial load right away. But I don't know how to get there. Where do we get joules from? We don't have any joules here.
I think this is one of those questions where I think this question is kind of classic MCAT in the sense that it takes a kind of straightforward physics concept and applies it in such a strange way to this passage that it kind of makes it incomprehensible. Where, I feel like this is a question where if you kind of phrased it to, the question that lies at its core more directly to someone, it becomes much more obvious. But kind of when structured like this, it seems almost inscrutable. But this is effectively asking, what is the work done by a force through a distance? Which is to say, that's the definition of work in this context, right? If we think about our formula for calculating work, the unit of which is joules, it is the force that is being applied multiplied by the distance it's being applied through, multiplied by the cosine of theta, where theta is the angle between the force and its displacement vector. So in this case, that sounds very complicated, but in this case, the fiber is being linearly deformed, which means what's the angle between the force that's being applied and the kind of direction, in this case, that the fiber is stretching in? Well, they're stretching and their force is being applied in the same direction that it's stretching. So the angle of separation between them is 0 degrees, and the cosine of 0 degrees is 1, so we can actually just completely ignore trigonometry here.
Nice. Thank you, MCAT.
So what this boils down to is just force multiplied by a distance, which is to say 10 newtons multiplied by 3 nanometers. Because this is asking for it in joules, joules does require that all of the units that go into it be in the form of kind of SI base units, so kilograms, meters, and seconds, or of course newtons and meters. So we can leave 10 newtons as is, but we would have to convert 3 nanometers to meters, which the conversion factor for that is 10 to the negative 9. This question reduces to 10 times 3 times 10 to the negative 9, which is 30 times 10 to the negative 9. That is to say, shifting over the decimal point, 3 times 10 to the negative 8. B is the correct answer.
Wow. So really straightforward question that obviously could use a lot of this discussion. So, all right.
If I had no idea here, or maybe if I didn't remember how to convert nanometers to meters, I would look at this question and say, well, the fiber is deforming, so there is some work being done. So I would eliminate A because it's probably not 0 joules.
Yep.
And then if I were guessing, I would say, well, we have 3 nanometers and I have 10 newtons. So whatever the right answer is, it'll probably be 3 times 10 to the something. And I would eliminate D, and then I would guess between B and C. Which of the following waves would have a wavelength larger than any standard electro-spun fiber? This is a great question. Oh, wow. How would you approach this?
Well, the answer is here: A, red light; B, blue light; C, microwaves; or D, X-rays. I would approach this by crying, clicking C, and moving on, because I'm like, wait a minute, where did we talk about waves of things, wavelengths of things? I don't know. I'm very sad.
This question is great because I feel like this is I say great. I'm someone who loves MCAT question design. I can absolutely imagine, right? I'm taking my first diagnostic test and I see this and like burst into tears. But I think this is like a classic example of how the MCAT phrases questions in a way that again makes them sound much more difficult than they actually are. Not to say this question is easy, but I think this question implies that you have to kind of figure out the diameter of an electrospun fiber and then have all of the wavelengths of all of these forms of light memorized. But remember that the MCAT's a multiple choice test, so only one of these answer choices can even be correct. Which means we can actually just rephrase this question as, which of the following waves has the largest wavelength? Because if there were two that had a wavelength larger than an electrospun fiber, I mean, both of them can't be right. So there'll be three here that are shorter, one that's longer. This question is just asking which of the following forms of electromagnetic radiation has the longest wavelength.
But so you say that with lots of confidence. This question is just asking blah blah blah. But it's trying to, the question is comparing wavelength larger than any standard electrospun fiber. Don't we have to know the standard electrospun fiber? Like, how do we just ignore that?
We don't, because only one answer can be correct. So if the question is asking which of the following waves is larger than X, well, if only one of them is correct, that is to say, only one of them is actually larger than an electrospun fiber, then the question's just asking which of the following has the largest wavelength.
Stupid reading comprehension, man. Like, I object to this question. Anyway, aren't microwaves really large waves?
Yep. I mean, they're not really large, but
compared to the other ones.
Exactly, right? You know, red and blue light, they're on the order of nanometers, and X-rays are even short. You know, X-rays are energetic enough to to
penetrate
break bonds. Yeah, exactly.
Yeah, the way that I answer this and remember about microwaves is we can stand an inch away from the microwave when it's in use and look through the tiny little holes because the waves aren't coming out of those holes because they're bigger than that.
Exactly. And in fact, if you put like a sheet of paper that like changes color in the heat in your microwave, it'll have like basically like little nodes and antinodes, like little hot spots and cold spots based on the wavelengths. And from that, you can like take the frequency of your microwave and like calculate the speed of light.
Nerd.
I know. Fun things to do with a microwave.
Yes. Don't put tinfoil in it. All right. Question 8. Assuming a mass of 0.04 grams, what is the power exerted by the electrical forces on a fragment of fiber if the fragment has a velocity of 200 millimeters per second, 10 milliseconds after ejection? So again, like, I'm just like, this is all physics. I don't want to bother with this. I'm done. Like, I hate you, MCAT. I hate you, diagnostic tests. I just want to quit.
This is and honestly, particularly for someone taking the diagnostic, I would say, look, if you get this question, particularly you're just starting studying for the MCAT, you have my complete permission to just flag this question and keep going, right? Guess, pick your favorite letter, keep going, like go through the rest of the section, come back to this at the end if you have time, because this question, I think, kind of requires a comfort with quick math that I think that not very many people possess when they first start studying for this test.
Yeah.
So I say to people, like, look, don't let a hard question stop you from answering an easier question at the end of the section. In this case, we have this is a power question, and power, the units of power is work per time. So the classic unit of power is the watt, which is a joule per second. You know, think of like a 60 watt light bulb, it consumes 60 joules of energy per second. In this case, we have the quantities that we need from the passage to answer this. We can calculate, in this case, the fragment is moving at a certain velocity, a certain speed after ejection. Remember that things have energy if they're moving at a velocity. They have kinetic energy. If we then say, well, it gained that energy over that 10 seconds, well, then the electrical forces are exerting an amount of energy in a window of time, which means we can calculate the power from that. The way we'd calculate it here is the formula for kinetic energy is 1/2 mv squared, where m is the mass of the object and v is its velocity. So in this case, its velocity would be 0.04 grams. Its velocity would be 200 millimeters per second, which converts, once we convert that to meters, is 200 times 10 to the negative 3 meters per second, and we'd have to square that. So once we had its kinetic energy, we could divide it by the amount of time that it took to accelerate to that speed, which is to say 10 milliseconds, or 10 times 10 to the negative 3 seconds. And once we do all of that math out, we'd end up with 8 times 10 to the negative 5 joules per second. That is to say 8 times 10 to the negative 5 watts, and D is the correct answer.
Wow.
Yeah, this is a tough question, and one of those rare-ish MCAT questions where you'd basically have to do all of the math. Looking at this off the top of my head, I don't think I would be able to eliminate any of these answers.
Yeah, this is one of the first times where on the MCAT podcast, doing reviews like this, I'm just completely like, I have no idea where to start. I have no idea what I should be thinking about. I have no idea. A lot of times I can start to rationalize where I should be going. And so I'm mad right now because I get into this diagnostic. I want to be a doctor. I get in here and then I'm just punched right in the face. And now I feel like an idiot because I'm like, what's going on? Why is this diagnostic, at least this passage, so much harder than almost anything else I've seen from Blueprint in terms of their full lengths?
From what it's worth, Blueprint has some pretty tricky passages. And this is certainly one of the harder ones, but it's not so much harder that, it's not, the hardest passage you'll ever see when studying for the MCAT. Certainly not.
Do you have the data in front of you? What percentage of students get it right or wrong? Do you have that in front of you or no?
I do. 46% of students got this one correct, which seems kind of hard to believe. This one's really hard, but I'm very impressed. But I would say if you approach this, if you're listening to this, you've just taken your diagnostic and you kind of ran into this passage like a brick wall, know that in a sense it's supposed to feel like that. Remember that the diagnostic, in a sense, it's not designed to be way harder than the real thing to scare people into studying more, but it's also not designed to gently ease you into the MCAT, other than the fact that it's half length, right? This experience of approaching a tricky question that requires some math, that has a lot of moving parts to it, that requires you to hold a lot of things in your head and kind of integrate from multiple sources of information. This is kind of at its core what the MCAT is. So it is very realistic in that way. And every MCAT will have, a handful of questions, or even a bit more that are kind of as hard as this, but they will seem easier with time as you become familiar with its conventions.
If you say so. All right. Question 9. I think it's your turn.
If all other factors are held constant, which of the following scaffolds would have the highest productivity? And what we get here are
Well,
just
go ahead and read the
values.
answers for that one.
Yeah, so we have A, which is M sub E, is 1 millimole. B, M sub E is 2 millimoles. C, M sub E is 3 millimoles. And D, M sub E is 4 millimoles. So that's it. 1, 2, 3, 4. Which one is the highest?
So I'm assuming it either has to be A or D.
Bingo. Perfect strategic deduction. Exactly. Which is like, look, if it's the highest, it's either going to be some sort of direct relationship or some sort of inverse relationship. And so the correct answer will lie on the extremes. I would eliminate B and C here immediately.
Yeah. So highest productivity. If we look at equation 1, I'm assuming efficiency and productivity potentially are synonyms here. And if I use that theory, M sub E is the denominator. And so the lower the denominator, the higher the answer. So I'm going to go with A, 1 millimole.
You would be correct.
Woohoo!
Quite for the right reason, but close.
I don't care. I got one right.
You got the one. I think you got the one like 2 questions ago right as well, because you guessed, you had like no idea and guessed C, but C was the right answer. And yeah, so in this case, efficiency and productivity are not quite the same thing, but they do relate to each other, like you said. In this case, efficiency, M sub E is in the denominator, so of course the lower that it is, the higher that efficiency would be. But productivity is that equation 2 down below, but efficiency is that epsilon is in the numerator.
Yeah.
So efficiency and productivity are directly related, which means that the relationship that M sub E has with efficiency is also true of its relationship with productivity.
Yeah.
So in which case, the correct answer would be the same.
Awesome. All right, got one right. Piece of cake. All right, I'm coming back. 5:20, 5:25, here I come. Question 10. Which of the following best explains why, at a constant voltage, warmer solutions are ejected more quickly than cooler ones? A, the droplets have smaller volume at higher temperatures. B, the surface tension is lower for solutions at higher temperatures. C, the electrical forces grow smaller at higher temperatures. Or D, the electrical forces grow larger at as temperature increases. So, constant voltage, warmer solutions ejected more quickly than cooler ones. So, the only thing I can think about is, again, just not knowing anything about what's going on in this passage and not knowing anything about anything. I go, you know what? When water temperature's higher, surface tension's a little bit lower, I think. Because water starts boiling if you get high enough. So B is the only one to me that's like, oh yeah, I kind of think I understand that. That's like boiling water. So I'm going to go with B and move on because I don't know anything else.
Perfect reasoning, and you got the correct answer.
See, the MCAT is doable if you just understand. Like, it's just a whack-a-mole. It's a whack-a-mole game.
And that's such a great demonstration of the fact that this question is interrogating, I'm not going to say easy, but like kind of a singular fact of liquids is that as their temperature increases, generally surface tension tends to decline. Mm-hmm. Surface tension is a property of cohesion, right? Liquids tend to stick to themselves. And as you increase the temperature, as you increase the average kinetic energy of a liquid, they will have a propensity to stick to each other less, because of course they become increasingly more likely to, break away and become vapor. And of course, if you heat them up high enough, they'll start boiling. And in this case, I would note in the passage that it would be possible for B to be wrong here if surface tension was just irrelevant to them being ejected.
Yeah.
But paragraph 1 tells us that electrospinning occurs when electric forces at the surface of a polymer solution overcome the surface tension. Well, if the surface tension is declining, well, then the electric forces should have an easier time overcoming it, and the solution should, all else being equal, eject more quickly.
Yep.
I think C and D are really tempting answers here, because D, if it were true, would be correct, but electric forces on the MCAT are unaffected by temperature.
Okay. All right. Passage 2 in the books. Did I get the last 2 right?
You did.
I did, but...
You got at least 3 of these right.
2. I'll go with 2. All right. So, again, to highlight, right, the importance of knowing everything on the MCAT is nil. You can't know everything. The importance of reading comprehension and using your little noggin up here and try to rationalize some things may make you wrong sometimes, but in my mind, more often than not, probably is going to get you in the right direction.
I think that's such a key insight, because so often, when students, particularly just off the diagnostic, right, they start their MCAT studying journey. We often, at Blueprint, get a lot of students that come to us and say, look, I know your study plan says that I should do all of this test-like practice, I should do X thousand questions, but I just don't really like doing questions. I get them wrong. I think I should just study content by myself for 3 months until I understand everything really well, and then I'll start taking full lengths.
Yeah.
And I often say to people like, no. The MCAT is not a test of your content knowledge. It's a test of your ability to get MCAT questions correct.
Yep.
And people, they're related, but they're not the same.
Yeah. Yeah. 1,000%. All right. Another episode in the books.